long-distance missions in space, like when NASA sent probes to explore the edge of the solar system, probes needed to provide energy to the equipment on board the probe to power the devices measuring, and then also to send back the signals, identifying what those readings were, back to Earth. Now, when a probe is close to the orbit of the Earth, its power can fairly easily be done by solar panels, which collect all the required energy from the sun. But on the edge of the solar system, there isn't enough energy provided by the solar panels to power all the required devices, and even using standard batteries isn't going to work, since the batteries would soon run out of power. So instead, space agencies resort to something which is called a radio thermic generator. Now, nuclear power is fairly efficient at producing quite a lot of energy for a relatively small amount of mass. But a nuclear reactor, even the small ones used to power ships on the oceans, are fairly large, heavy and complex systems that would be almost impossible to get into space on a probe, let alone the issues with maintenance. However, nuclear power can still be used in a fairly simple way, but practically to put into use on a probe. You get some radioactive plutonium-238, which has a half-life of about 87.7 years. You have an energy source which, even though it will gradually get weaker over time, will still be releasing energy decades later. The problem is you have to how to use that energy, and how can you actually turn it into something useful you can use on a probe. The answer, of course, is to use a radio thermic generator, which, as the name suggests, is to use the heat created by a radioactive source to generate electricity. It uses something called the thermoelectric effect. Basically, when you heat up one side of a conductive material, it creates an electromotive force in the material, so electrons will flow from one side to the other, similar to how a battery operates. This will continue so long as you have the energy source which was able to heat up one part of the material. And it's fairly useful on a probe. For normal purposes on Earth, using plutonium-238 to create something similar to a battery is never going to be a practical solution, as it's far too dangerous. So there's a similar method we use to make a much safer nuclear battery. There are three main types of nuclear radiation: alpha, beta and gamma. And of these, gamma radiation is the most dangerous, as it can penetrate through substantial distances through solid objects, including the human body. And large amounts of lead are currently the best protection we have against gamma radiation. As an isotope of nickel called nickel-63, which has a half-life of around 100 years, and in the decay process it releases beta radiation, a form of high-energy electron. If beta radiation came in contact with human skin, it could potentially be very dangerous, but thankfully beta radiation can be stopped by a thin sheet of metal, so it's possible to produce a relatively safe device using beta radiation, so long as the device was properly disposed of when it's finished with. Now, if you pair the nickel-63 with a semiconductor, the semiconductor will absorb the electrons produced by the nickel, and that semiconductor can then release the power from the electrons when needed. Again, you have your nuclear battery. Again, like the radio thermic generator, these batteries have potentially been used on space missions. The additional advantage that these batteries are believed to be able to withstand dramatically high temperatures on Venus or some other missions, and still produce power for a device. Now, back down on Earth, there's also a possibility for a more mundane use for these batteries. So while they don't produce the same voltage as standard batteries, potentially they could keep going for 50 years, still producing energy to power a pacemaker or some other device which needs to be constantly on but using minimal power. As long as the battery remains intact, it will be perfectly safe, as just the casing of the battery would produce enough shielding to protect against radiation. The disposal at the end of the life of the battery would be an issue. And while nickel-63 is currently the focus of these beta-voltaic batteries, the energy source could be tritium, carbon-14, promethium-147, or a handful of other isotopes.